Okay, probability and a binomial distribution. First part, which is tree diagram, is an easy bit, then we'll go on to some binomial thoughts in a second. What we have is we roll 2 dice. And what we're looking for is success is when we get one of them a 4 and the other one anything else. That's what we're after on our tree diagram. 1/6 probability of a 4, therefore 5/6 probability of not. Roll a second dice. Probabilities will stay the same. 1/6 for getting the 4, 5/6 for not. And combinations we're looking for exactly 1 4, so 4 or not a 4, that's good. Not a 4 or 4, that's good. And follow and multiply to work out the final probability. So 5/36, the chance of that first combination. And if it happens the other way around, 36. So the probability of our event happening, our event is getting exactly 1 4, is these two. 10 out of 36. In other words, 5 out of 18 is the probability of getting exactly 1 4 when we roll 2 dice. Moving on. Binomial distribution. We've just considered a very simple case of that. We'll consider a more involved one here. A binomial distribution is when we're dealing with some probabilities of a success-failure situation. Something can happen or not happen. One of two things. That's binomial. In this case, we get that single 4. Now, if we roll the 2 dice, we could get the single 4. Get it again, get the single 4. Then we could fail to get the 4, fail to get the 4, and that would be good. We would have got exactly 3 successes. And the probability of getting that would be, well, 1 success, 1 success, success, failure, of course, 13/18, 1 minus 5/18, failure again, and a probability of 3 successes followed by 2 failures would be that. But why am I not just working that out to get the answer? Well, the problem with this is it could happen in different orders, different combinations. That, for example, or even that, for example. So our problem here is, although we'll always get 3 successes, 2 failures in all of these combinations, and any more we could think of. Our question is, how many different ways can this happen? The best way to deal with this is with our idea of combinations. 3 from 5, choose 3 from 5, and this NCR calculation, combinations calculation, can be done easily on a calculator. Let's do that. On the calculator, what we're looking for, option, probability, NCR. Most scientific calculators have this combinations button. So 5 events and choose 3 from 5, 3 successes. How many ways? 10 different ways is the number. I'm going to go through and just multiply this all together to get my answer then. So just forgive me while I just key this all in. So 5/18 power 3, 3 successes. 13/18 power 2, 2 failures, 10 different ways, and there's my answer. 0.112. It's my answer to this one here. Better ways to do this. Well, one of the ways we could do this is to try and get the calculator simply to do all this for us, so we'll go back to the calculator. I'm going to go to my statistical analysis here, distributions, binomial, and I've got 2 possibilities. One of them will work out single probabilities of getting 3 successes, 4 successes, etc. The other one will add up probabilities together. I'm just going for a single one in this first question. The add them up will come in the second part. So first button, BPD, single probability. I'm just going to choose variable. I'm just going to give it the number. I'm not going to take it from one of my lists. 3 successes. number of trials 5, the probability of success 5/18, and if I run that, 0.112, exactly as we got there. Right, moving on, verified. I mean, we could do that first part in either of those ways. To consider this second bit, importantly, what we've got to realise here is that probabilities, we could get no successes, of course. 1 success, 2 successes. A little laborious, but bear with me. This is the kind of crux of the issue here. And with binomial distributions, we could go through and we could look at all the successes. We have got this one here for the moment, 1, 1, 2. Now, if we want at least 3 successes, then we've got to include this one and this one as well. Back to the calculator. Let me change that to a 4. So 4 successes. 1.021. Back to the calculator. 5 successes. 1.0017. And put all these together. 0.135. There we go. 0.135, that includes the 3, 4 and the 5. Now that's all very well. We've answered this question now, but it's worth just noting that we've got another option on our calculator to do this, which would be very useful if we wanted to put a lot of these together. Clearly, if we've got lots of individual ones we want to add up, we don't want to do them all individually. So, back to the calculator. And back to our distributions, binomial, and this second button, this cumulative probability button, C for cumulative. If I press this, it looks very much like the last screen I got. However, when I choose a number now, what it will do is it will start at the beginning and it will simply add up as it goes, so it'll put them all together. I am going to put 2 in there. The reason I'm going to do this is that I can't start midway through the distribution. I've got to start at the beginning. So I'm going to do that trick in probability where you add up the ones you don't want before you get the ones you do. So a cumulative probability of 0, 1 and finally 2 off my calculator here. And it is telling me that if I go as far as 2 in the distribution, then I will get the answer 0.865. And if I'd have used this answer, the probability of getting greater than or equal to 3 would have been 1, everything, minus the ones that I didn't want. And that would have given me the 0.135 that I kind of knew already. So there we go, several different ways of getting our combinations and our binomial probabilities.